Section: Introduction. In this section, we explore the concept of bringing text to life through motion. By animating text, we can convey emotions, emphasize meanings, and create dynamic narratives, transforming static messages into interactive experiences. This fusion of motion and text captivates viewers and enhances the impact of the message in various media such as movies, advertisements, websites, and memes. Our focus is on animating individual letters within words, a task we call dynamic typography. For instance, we can animate the letter M in the word camel, based on a prompt like, "A camel walks steadily across the desert." This approach enriches the reading experience by adding a new dimension to text. However, creating such detailed and prompt-aware animations is challenging for non-experts due to the complexity of traditional graphic design methods. Our technique aims to automate this process, making it more accessible and efficient. We represent each letter and frame as vectorized shapes using Bezier curves, allowing for clear and editable text regardless of scale. To address the challenges of animating vectorized shapes, we introduce an optimization-based framework using neural displacement fields. These fields deform the original letter and define the motion applied to it in each frame, ensuring legibility and consistency throughout the animation. Our approach includes techniques such as high-frequency encoding of control points, perceptual loss regularization, and shape preservation based on triangulation. These methods maintain the legibility and structure of the text during animation. We demonstrate the effectiveness of our framework through quantitative and qualitative tests, showing that it accurately interprets input text prompts while preserving readability and alignment with the prompt descriptions. Compared to static text stylization techniques like artistic text style transfer and semantic typography, our dynamic typography approach stands out by infusing text with vibrant motions that effectively capture attention and convey meaningful messages in a visually appealing manner. Section Summary. In this section, we introduce a specialized text scheme called Dynamic Typography that focuses on animating individual letters within words to convey semantic meaning through vivid movements based on user prompts. Our approach utilizes an optimization-based end-to-end framework with neural displacement fields and high-frequency encoding to automate the animation process, ensuring readability and coherence in the generated text animations. By quantitatively and qualitatively testing our method against various baselines, we demonstrate its efficacy in producing coherent text animations that accurately interpret input prompts while maintaining the legibility and visual appeal of the original text. Section: Dynamic Text Animation. In this section, we explore dynamic text animation. We have seen that dynamic texts are effective in capturing and holding audience attention. Researchers have been working on creating dynamic texts, especially in dynamic style transfer. This involves adapting the visual style and motion patterns from one video to another. Initially, researchers transferred styles from videos displaying dynamic texts to static texts. Later, they improved this by using a scale-aware shape-matching GAN to handle different input styles. Kinetic typography is another exciting area where motion is integrated with text to convey a message effectively. However, creating kinetic typography is challenging and time-consuming, leading to efforts to simplify the process for everyone. With advancements in AI, we can now automatically generate kinetic typography. For instance, a model uses a pre-trained motion transfer model to apply patterns from a meme GIF to text. But these methods often require specific videos as input, limiting their practicality and ability to generate complex motion patterns. In contrast, our method can handle various motion patterns with just a text prompt as input. Moving on to text and image to video generation, the goal is to automatically create videos based on textual descriptions. Recent advancements in diffusion models have significantly enhanced video generation capabilities. Some approaches incorporate temporal information in a latent space using stable diffusion, SD. Beyond text to video generation, some methods aim to generate videos from images and prompts. While there has been progress in this area, maintaining text readability during motion remains a challenge for open-source video generation models. Training a model to generate high-quality, readable dynamic texts would require a large dataset, which is often hard to obtain. One recent work, Live Sketch, focuses on animating vectorized sketches without extensive training. However, when dealing with vectorized letters, Live Sketch struggles to maintain legibility and consistency during motion. In contrast, our method excels in generating consistent and prompt-aware dynamic texts while ensuring text readability. When it comes to vector representation and fonts, vector graphics create visual images using geometric shapes, allowing for infinite scalability and editability. Modern font formats like TrueType and PostScript use vector graphics to define glyph outlines, typically using Bezier or B-spline curves. Our method outputs frames in the same vector representations as the input, ensuring scalable and flexible text rendering. We use the FreeType font library to extract outlines of specified letters, converting them into closed curves composed of cubic Bezier curves for a coherent representation across different fonts and letters. Lastly, score distillation sampling, SDS, leverages pre-trained diffusion models' knowledge for text condition generation of different modalities. SDS optimizes the parameters of a parametric generator to align the output with the prompt. By utilizing SDS, we can extract motion prior from a pre-trained text-to-video diffusion model, even though SDS is typically used with raster images. To handle this, we employ Diffvg as a differentiable rasterizer to convert vector-defined content into pixel space for applying the SDS loss effectively. Section Summary. In this section, we explore dynamic text animation, focusing on dynamic style transfer and kinetic typography techniques. We discuss advancements in AI for automated kinetic typography generation and the challenges of strictly specified driven videos in real-life scenarios. Additionally, we delve into text-to-video generation methods, emphasizing the importance of maintaining text readability during motion and the use of vector representations in font rendering. Section: Method. In this section, we focus on animating individual letters within words based on the user's input. We start with deforming the letter to represent the word's meaning and then adding motion based on the user's prompt. The original input letter is set as a group of control points on a cubic Bezier curve. These control points have coordinates in an SVG canvas, with the total number of control points denoted as n. The output video consists of multiple frames, each frame represented by a set of control points. Our aim is to learn a displacement for each frame, which is added to the original letter's control point coordinates to show the motion based on the user's prompt. To achieve good results, we have three main requirements for dynamic typography. 1. Temporal consistency. The deformed letter should move smoothly while maintaining a consistent appearance in each frame. 2. Legibility preservation. The deformed letter should remain readable in each frame. 3. Semantic alignment. The letter should be deformed and animated in a way that matches the semantic information in the text prompt. One approach is to first deform the static letter using existing methods and then use a model designed for graphics made of Bezier curves to animate the deformed letter. However, this method can lead to visual artifacts like distortion and inconsistency. To address this, we propose an end-to-end architecture that directly maps the original letter to the final video. To handle the complexity of learning per frame displacement, we represent the video as a learnable base shape with motion added on top. We also include legibility regularization and structure preservation to maintain the appearance and integrity between frames. Additionally, we use encoding techniques to enhance the representation of geometry, information, and motion quality. We introduce two neural displacement fields, the base field and the motion field, to model the generated video. The base field learns a shared shape for every frame, serving as a base for adding motion. The motion field encodes the relationship between the control points in the base shape and those in each video frame. We decompose the motion into global and local components to better model the displacement for each control point. To train the base field and motion field, we use prior knowledge from a pre-trained text-to-video model and optimize using a differentiable rasterizer. We apply legibility regularization and structure preservation to maintain a consistent appearance throughout the video. Section Summary. In this section, we propose a method called Dynamic Typography that animates individual letters within words based on user prompts. By deforming letters to represent semantic meanings and infusing motion based on user input, we aim to create visually appealing videos. To achieve this, we introduce an end-to-end architecture that directly maps the original letter to the final video, addressing challenges such as maintaining temporal consistency, legibility, and semantic alignment. By utilizing neural displacement fields for base and motion representations, we can learn per-frame displacements to convert input letters into animated frames while mitigating visual artifacts like distortion and flickering. Section: Legibility regularization. In this section, we focus on ensuring the legibility of text and preserving the structure of the mesh in our dynamic typography model. We aim to make sure that the text remains readable and that the mesh structure is maintained throughout the optimization process. To maintain legibility, we introduce a regularization term that works alongside the SDS loss. This term enforces the text to be legible by using Learned Perceptual Image Patch Similarity, LPIPS, to measure the perceptual distance between the base shape and the original letter. By applying this legibility regularization to the base shape, the motion field automatically propagates this constraint to each frame. Next, we address the issue of complex intersections between Bezier curves that can occur during optimization. These intersections can lead to visual artifacts like black and white holes in the image and flickering effects between frames. To tackle this, we adopt Delaunay triangulation on the base shape to maintain the mesh structure. By regulating the angle variation of the triangular meshes between adjacent frames, we prevent frequent intersections of Bezier curves and ensure consistency in local geometry information. Furthermore, we apply frequency-based encoding and annealing to capture both low and high-frequency motions effectively. By using sinusoidal functions and weights for different frequency bands in the positional encoding of MLPs, we can represent detailed geometric features and achieve higher quality motion in our model. Section Summary. In this section, we introduce two key regularization techniques for improving the legibility and structure preservation in dynamic typography. To maintain legibility, we propose a regularization term using Learned Perceptual Image Patch Similarity, LPIPS, to ensure that the letters remain recognizable throughout the animation process. Additionally, to preserve the structure of the typography, we implement Delaunay triangulation on the base shape to prevent complex intersections between Bezier curves, ensuring a stable appearance across frames while minimizing flickering effects. Section: Experiments. In this section, we conducted experiments to evaluate our method thoroughly. We made a dataset covering all letters of the alphabet, including animals, humans, and objects, with a total of 33 dynamic typography samples. Each sample consists of a word, a specific letter to animate, and a brief text prompt. We used Caution Script Regular as the default font and the text-to-video MIS 1.7b model in model scope for the diffusion backbone. Augmentations like random crop and random perspective were applied to all video frames. Each optimization process took about 40 minutes on a single H800 GPU for 1000 epochs. We showcased some generated results to demonstrate how our method brings the specified letter to life while maintaining the word's readability. For more examples, we recommend exploring additional samples and full-length videos on our project page. To compare our method, we looked at two categories: pixel-based strategies using text-to-video or image-to-video methods and vector-based methods. In the pixel-based category, we compared our model with Gen 2 and Dynamicer. For the vector-based comparison, we used Live Sketch. Our model strikes a balance between aligning with the prompt and maintaining letter legibility, unlike other methods that struggle with either movement realism or legibility. We also conducted a quantitative evaluation using perceptual input conformity, PIC, and text-to-video alignment metrics. Our model excelled in preserving the original letter's form while aligning well with the prompts. An ablation study was performed to analyze the impact of different components in our method, such as learnable base shape, legibility regularization, structure preservation, and frequency encoding with annealing. Removing these components resulted in decreased legibility, structure preservation, and overall quality of the animations. Section Summary. In this section, we conducted experiments to evaluate our method's performance using a dataset covering all alphabet letters with various elements like animals and objects, totaling 33 dynamic typography samples. We utilized the Caution script regular font and applied augmentations to rendered videos, achieving high-quality results that vividly animate specified letters while maintaining word readability. Comparisons with existing methods showed that our model excels in preserving letter form and alignment with prompts, striking a balance between legibility and prompt video coherence, as demonstrated in both qualitative and quantitative evaluations. Section: Generalizability. In this section, we demonstrate the generalizability of our optimization framework using score distillation sampling, SDS, across different diffusion-based text-to-video models. We tested various base models, such as the 1.7 billion parameter text-to-video model from ModelScope, AnimateDiff, and ZeroScope, to compute the SDS loss, L_SDS. Visual results in the figure show how each model interprets the same sample, night. Although each model displays unique deformations and styles for the letter K, they all accurately represent the user's input and maintain the fundamental shape of K. This highlights the ability of our method to generalize effectively. Therefore, as text-to-video models advance with more prior knowledge, our approach stands to benefit from these improvements.